All right, so welcome back. So what I will do, as I mentioned earlier, is this particular theory, the so-called five-fourth field theory, is at the heart of so many things in physics, um, starting from the theory of classical phase transitions, and then going on to the theory of quantum phase transitions, the conformal field theories, and so many developments uh, that follow from here, including then the Hertz theory, which was added Fermi surfaces to this. And just studying all that has been a focus of so much uh, physics in different areas that I thought I'll just at least review the original classic calculation of Wilson and Fisher that told us what are the properties of this theory in all dimensions D. So I'll think of just a space and time will be the same. So D is the space-time dimension if you're thinking of some quantum model, or D is the spatial dimension if you're talking about a classical phase transition. So the starting point here is the Landau-Ginzburg theory, which is exactly this theory. And what Landau-Ginzburg did was just minimize this functional. Everything they did was just completely equivalent to minimizing this functional. You can add a magnetic field, and then you get vortices, and understanding those vortices led to a Nobel Prize for Abrikosov. And so the list of Nobel Prizes you can make that followed from understanding this theory in different situations is very large. But we want to now understand something about the full path integral of this thing, d phi of x. And this is some partition function. We want to understand some of its properties beyond the Landau-Ginzburg mean field theory. So I will do this. Is that okay? I think that'd be a useful thing to do. And if there's some time left over, and unless somebody objects, I want to just talk about some recent work on how to apply this, the theory of strange metals to the cuprates, which I told you in the end, and it doesn't apply because there's no spin density wave order in the Holdt cuprates. But using spin liquids, I want to give a very brief discussion of spin liquids. Okay, all right. So that's what I'm going to do. That won't be a tutorial, and unless the organizers forbid me from doing it, I will do it. Okay, so let's talk about this theory. So this theory, if I just do what Landau did, then you get, just look at the potential. Think of this as V of phi, some potential for phi, and you want to minimize it, assuming phi is spatially independent, and then the potential looks something like this as a function of S. There's some critical point where this is for S less than SC, the potential looks like this, and so you pick one of these minima, and then you break the symmetry, and on S greater than SC, it looks like this, and then you just have one minima, and then you have a symmetric phase. This is a broken symmetry phase. Okay, so this is V of phi. All right, but what about what happens exactly at the critical point? Well, exactly the critical point where S is 0 in the mean field theory, this becomes very flat. And so it's phi to the fourth. And so we have to really worry about fluctuations. How singular are they? And what was found was that the key thing was this dimensionality, that for d greater than 4, fluctuations were not important, whereas for d less than 4, they are very important. Okay. And I just want to go through the RG argument that shows that, and also show you how for d close to 4, there is what's called the epsilon expansion that allows you to compute a few things and understand something. All right, so how does this all work? So if I imagine doing perturbation theory, then the perturbation theory, I'll have a propagator for phi, just take the quadratic part and do perturbation theory in U, then the propagator for phi will look something like this. This will be the propagator for phi, some line for phi in perturbation theory. And so we see that, when S goes to 0, this propagator is becoming very singular. But it also has a factor of momentum here. This k squared is coming from this term. And so this means that at least at large momenta, nothing is happening. But at small momenta, something is happening. So now to define the theory as written, you need some cutoff. So there is some cutoff here, lambda, which is implicit in this integral, meaning that every time you do the path integral over phi, you're integrating in momentum space, in d-dimensional momentum space, k. You're restricted all integrals to below some cutoff, lambda. Okay. So the idea of renormalization idea of Wilson was the following. He said, yes, it's true that when S becomes very small, the very low energy modes are all disappearing, are getting very, very singular, very small K modes. But the large K modes are not. So let's just do it step by step. Let's just integrate out the large K modes. Then everything should be quite unsingular, because this propagator is still pretty small then when K is large. And so by step, he means we're going to take a little momentum shell, as it's called, of radius lambda minus d lambda. Okay. So when you're doing this path integral over phi, I'm going to do it in 2 steps. I have phi, which is sitting here, which I'll call phi lesser, and phi, which is sitting here, which I'll call phi greater. I'm only going to do the integral over phi greater. And everything should be well defined, because phi greater, this k is equal to lambda, pretty much, when d lambda is small. So perturbation theory should be good, at least for small u, no matter whether S is 0 or not. Even when S is 0, everything is fine, because there's a lambda squared over here. Okay, so you do that. What have you gained? Nothing. You just just change the theory a little bit. You still haven't understood the critical point, because the hard part is what's happening in here. What about these modes? These are the ones we need to understand. Okay, so the key idea is that this is actually sufficient, provided we do this over and over again. So you do step 1, then you do it again. But now the point is that when you do it, step 1 is you integrate this out. So that's step 1. So this is step 1. But then step 2, so now this is gone. So now you have a theory where these modes don't exist. But you have a new theory with a different cutoff. Step 2 is you're going to rescale lengths and momenta. And also the fields. So you're going to rescale. K is going to go, and the way we say this is we're going to put a renormalization factor of S. K is going to K times S, so that lambda minus d lambda goes to lambda. So in other words, S times lambda minus d lambda is equal to lambda. Thank you. It is not the same as. So let's call this R for now. Since I'm calling space X, there's no. Yeah. Okay, so we're going to scale everything, K all momenta by the factor of S. Now, even at U equals 0, when we scale momenta, we have to scale, of course, length. So here are the rescaling steps. One is K goes to S times K. So lengths have to go in the opposite direction, go into X over S. And even at U equals 0, this means we have to rescale the fields and the rest of this thing so that everything looks exactly the same. So that's the point. I should say that. Rescale lengths, momenta, so that the final form of the path integral for phi less than has the same form as the original path integral for phi. Okay? But at cost of changing some of the coupling constants. So then the reason this is a good thing, we rescale everything, so everything looks the same as before, then coming back to step 1, we don't have to do anything new. We just do the same thing over and over again because you've got the same theory to begin with. We scale length, so this theory went back to the original theory. And we keep doing this forever and see what happens to the couplings and the fields as you do this rescaling an infinite number of times. And the key insight of Wilson was that sometimes when you do this an infinite number of times, there's certain fixed points. There's certain fixed points where the rescaling doesn't change anything. You come back to exactly the same theory with the same couplings. And those fixed points are the critical points. That point where everything is fixed gives you this critical point, and it has all kinds of rescaling symmetries. Today we know they also have not just rescaling, it has also conformal symmetry in many cases. And all of exploiting those symmetries of the rescaling transformation is what has led to so much insight on the structure of this theory. And ultimately also to ideas on Planckian dissipation. Okay, so this is the basic rescaling operation. And so now we can, just looking at this, we can see how phi has to go. So there's no coupling constant here. So phi has to be rescaled so that this thing retains the same form. And you can just see from there that phi has to go, let's see. Let me see, you get d minus 2. You get d here, you get 2 here, minus 2 from the gradient, and then you have to take 1/2 of that. And I just have to remember which way it goes. So phi goes to phi times s to the d minus 2 over 2, or it's negative. What is it? Scaling dimension of, I have a different way of doing it. It's d minus 2 over 2 is the scaling dimension. So it is the negative. No, is it? So x goes, that gives you d in the denominator. So phi has dimension d minus. No, I think, is that right? Yeah, I think that's correct. Let me, d has dimension d minus 2 over 2. Yeah, no, that's correct. It was correct originally. Okay. So if you make these changes, you can just check that this goes back to itself. Okay, then how about this one? So now that goes back to itself, this won't go back to itself under the transformation, step 2, but R will have to change, therefore. So your coupling constants also have to change. And R will go to S squared times R. And then the theory looks exactly the same, provided you rescale R. So obviously this theory at U equals 0 is not a fixed point. R is going to rescale, except suppose R was initially 0, then it goes back to 0. So the only fixed point of this very trivial theory is R equals 0. All right, so now we apply the same thing to U, this step to U. What is the rescaling transformation? So U goes to what? Well, if phi goes to S to the d minus 2 over 2, so anyway, I think I remember this. It's 4 minus d. So you put in this transformation here, and you ask that U goes back to itself. then the dimension of U is basically, anyway, yeah. So the way this is sometimes written, you don't want to keep all these S's around. People talk about the scaling dimension. So there's something called the scaling dimension. And you would say that, and you put a little bracket. So the scaling dimension of K is 1, always, by definition, in any RG. And so the scaling dimension of X is always -1. And the scaling dimension of S, at least at this simple theory, is 2. Is 2. The scaling dimension of phi, of U, excuse me, U is 4 minus D. Yes.
R should be also D, right? Somewhere.
What?
The R, you wrote just 2. Shouldn't be like 2 minus D?
No, it's 2. Well, you can just see that here. You know, if the scaling dimension of this is 0, because we've chosen phi to say that this doesn't change, then there's an extra gradient that gives you a 2. That's all. It's always 2. All right, so you'll, many papers just say, okay, scaling dimension, and then you're done. This is what they mean. Okay. Now you can already see by this simple argument why this might be correct. That for D bigger than 4, why is Landau basically correct? Well, the point is that we've done this scaling, and we got the same theory back, and so far we have just ignored the effect of U, which is fine when U is 0. We assumed U was small. So if U is small, essentially very close to some small value, this is the entire scaling transformation we are done. But under the rescaling, what we see is that U becomes even smaller, because when D is bigger than 4, this is some small factor. So U becomes smaller and smaller and smaller and just disappears. And so for D greater than 4, we don't have to worry about the effects of U, because eventually it will go to 0 anyway. So that's essentially the simple argument, as simple terms as you can write down. But this tells you, but for D less than 4, which is the world we live in, things are not good. U is going to go after infinity. So what can we do? All right, so we have to now do something better. All right, so I said here that, in step 1, I integrate out the phi greater. But when I integrate out phi greater, I assumed nothing happened to the theory. So in fact, what I've done so far, if I write it in terms of actions, I have a partition function, which was, d phi lesser, d phi greater, and it's e to the minus some action of the lesser fields, S1, let's call it, S greater of phi greater plus S of phi lesser, and then I have some interaction term, let's call it I, which involves both phi lesser and phi greater. So if you just put phi equals, has all these different momenta, and you expand this out, quite generally you can write it this way. So now I just do the integral over phi greater, and I said I'm going to get a theory just for phi lesser. I do this integral. So this theory will, of course, have this term. That term, S of phi lesser. That will come exactly through because it doesn't involve phi greater. And what I assume that when I do this integral for phi greater so far, that all it does is give you some number which is independent of phi lesser. Because when you do this integral, you just get back the same theory. But in fact, you don't because of this term. So there will be a correction. What I haven't computed here, there's going to be some delta S of phi less. I have not computed this, which is going to come from this interaction term. And this interaction term is only present because of U. So let me call this S sub U then. It's only the U term that gives you this interaction. So where one component can be lesser and the other can be greater, that can come over here. They can't come here because phi conserves momentum. The two phi's here have the same momentum, so cannot couple lesser to greater. But this can, as we'll see in a minute. And so there's a change. So this is the one thing I have not done in writing this down. There's a further change in R and U because of this. Okay? So I have to compute this. That's the one thing left, and now pretty much be done. Okay, so that's the step. We're going to now go back to step one and do it a bit more carefully. Okay, so we'll do that using diagrams. So we're just going to integrate out phi greater and see how it normalizes things. So from this, we can ask, is there any term that's going to change R? So what is R is the coefficient of phi squared. So there is a term like this. So you look at this graph. So this graph has a lesser here and a lesser here, and a greater here. And this is U. So this graph is going to give me a change in the value of R. Okay, so I had an R earlier in the coefficient, and when I add this in, R will go to R plus delta R. So this delta R will come from delta S. And what is the value of delta R? Something we can compute. It's just this graph. So delta R, well, this comes with a minus sign because of minus U. There'll be some factors. And then there'll be an integral over momenta, d dk over 2 pi to the d. And this will go from lambda minus d lambda to lambda, because this is only the greater momentum, which is in this shell. And then I have the propagator, which is essentially lambda squared plus r. Okay, so that's the value of delta r. And so here there's a term here, which is delta r times phi lesser squared. There's such a term in this action, and it's just given by this graph. It's this term. Now, there's actually a coefficient here, which you have to work out. It takes a little bit of numerics, and I think I happen to remember it. It's n plus 2 over 8, where n is the number of components. Anyway, don't trust that. But there is some number that happens to do with the combinatorics of this graph. N is the number of components of phi. But, okay, yeah, 1/3. Then finally, is there any change to U? So this is the key thing. R, fine. We can tune R to be 0, fine. But what about U? U is the troublesome thing. Can we stop its flow off to infinity? And the answer turns out to be remarkably yes. So what is the renormalization of U? It's this graph. Okay, so this is a U here and a U here. This is greater. Everything inside has to be greater. Everything outside has to be lesser. And I've forgotten the number here. I'm getting old. But this is also negative. It's minus some number, U squared. And now we'll have d dk over 2 pi to the d, or 1 over lambda squared plus r whole squared, coming from these two. Okay, and that's pretty much it. Now you might legitimately ask here, since you're doing all of this, there also could be other graphs that you're going to generate. The graphs like this, where you have 6-point vertices. How about this? So here you have everything is lesser outside and greater inside. This is also allowed. So you're going to get a phi to the 6th term, and you get infinite number of terms. So what the hell are we doing? Well, suppose I had a term in the action, which was, say, often it's called v phi to the 6th. Then v, you can again work out its dimension, and that turns out to be, well, it'll be something 6 minus d, I think. It'll be s to the, which way does it go? 6 minus d, or yeah, it's always d minus 6 becomes something like that, and so on. So what happens is that when you're below 4 dimensions, only u starts to run off to infinity. V and any other term does not. So that's another thing you suddenly realize, which Landau had not appreciated at all. Well, he had in a different way, that you can just stop right here. You don't have to go beyond phi to the 4th, because everything else goes to 0 except the u. That's the only troublesome term, provided you're below 6 dimensions or something, below 4 dimensions. Yeah. Well, I'm assuming d lambda is small, so just put k equals lambda. Okay, that's all. All right. So in the end, all I'm going to need, really, to leading order is that this is going to be some number minus some, let's call it a, some number a times u times d lambda. And this is going to be some number b times u squared times d lambda. It's a small thing. It's a correction, but it's correcting everything, okay? So now I have to change the flow. So, you know, I have to do something else here. So R has this S squared, but I have to also, what should I have to do? So now my new R has 2 changes. It has this change, and it also has this change, okay? So my new R is this correction, and I'm sorry, this correction here. So let me try to get all the factors of 2 and everything correct up to this. So what will I get? So we're just going to work to first order, and we're going to assume d lambda is small. So let's see. So if I go back to this thing here, S is actually pretty close to 1. S times lambda minus d lambda is lambda. Now we want to do this transformation over and over again, so we want to write it as a differential equation. That's what the RG equations are. So we're going to introduce some notation. So I'm going to say I'm going to write d lambda is lambda times e to the minus dl. The dl is small. No, sorry. Lambda minus d lambda is lambda times e to the minus dl. And then, so S will just become, S is greater than 1, right? E to the dl, which is small, some differential. So now I have an R. So the new R at L plus dl is equal to, from here, you'll see you'll get basically e to the 2dl times r. That's this r. So this is r of L plus dl in the new theory, when I've changed the cutoff once. This is one correction. And then I have this correction here. Let's, again, put the, I can just write it as, absorb the lambda in A. So this is just e to the dl. No, just dl, sorry. That's the change. So there I have a term minus u times dl, and then u of L plus dl will be 4 e to the 4 minus d times u times dl minus u squared. There's an a here and a b here, some numbers times dl. So this is just the rescaling term, and this is the term coming from those graphs. And then you just expand for small dl, match the terms for small dl on the left and the right-hand side, and you get a differential equation. So now you get the famous Wilson-Fisher equations, which are the RG equations of this model, to leading order in one loop graph. These are the one loop Wilson-Fisher equations. Of course, they've been worked out to 6 loops now, and they are dr dl equals 2r minus some constant times r, and du dl is 4 minus d. I hope I got the signs right. Yeah, I think I did. 4 minus b times u squared. And there are, of course, corrections here. Assuming r and u are small, so their corrections are higher order than r and u, and similarly here, at u cubed and so on. All right, so fine. At least for small u, we've got a correction. So, but if u is running off to infinity, well, then how is this going to help anyway? Because I'm only working at small u. So this is where if you look at the original paper of Wilson and Fisher, the title of the paper is "Critical Phenomena in 3.99 Dimensions." So they said, we're going to solve the problem when d equals 3.99. Amazingly, when you solve the problem, and so they define epsilon. This is the famous epsilon, which is equal to 4 minus d. And you're going to solve it to first order in epsilon. I'll show you how they did that. And and if you take that first order result and compute certain quantities, and you put epsilon equals 1, for many things, including the critical exponent of the 3D Ising model, you get pretty accurate results. So this is one of those expansions, even though the very modestly said is 3.99, it turns out to be extremely accurate. And today, with some very sophisticated method, you can even apply it at epsilon equals 2. And it agrees there with Onsager's result and so on. So that's a very long and impressive story. But now let me just finish by telling you, so now all we have to do is solve these equations and see if they have any fixed point. Okay, so let me see if I get this right. So if you just solve those equations, and so they give you some flow in the RU plane. Okay, so let's see. So this is, we're going to draw this as a function of u and r. U will always be positive, but r can have either sign. Yeah. U negative is just unstable, so forget about that. The theory is not well defined. But u has to be positive. So what does this flow look like? Well, first of all, you can ask, are there any fixed points? And indeed, there is a fixed point. There's a u here, excuse me. There should be a u here. No wonder it was confusing. Yeah, there's a u. So there's a fixed point. This thing has a beautiful fixed point. Just look at the u flow. Du dl is 0, where this is epsilon. So there's a fixed point at u star right here. Okay. Yeah, all right. This may not be perfectly correct. There are some higher order terms that I may have forgotten. But, that's fine. There's a fixed point here. And this is at u star. And u star is equal to epsilon over b. Okay, so if we look at the flow of u, this is u equals 0. It flows this way. And on this side, it flows the other way. So for small epsilon, there's a fixed point which is very close to the origin. So you can trust the flow. And if you go to near this point, you can still trust the argument. It's fixed point. And if you go above, it comes back. All right. Okay, so that's the flow of U. There's also, there's a little tilt to that axis if you put in higher order terms in R, which I have not put. And if you look at the flow of R, well, that has, that flows away from R equals 0. And, at least at this point where U, so at this point, you will find that the flow of R looks something like this. It flows this way here and this way here. Whereas on this time, it flows like this. Right, so there's some flow like this if you draw the flow lines, if I get this right, like this. And then down here, it flows this way. Okay, I may not have it precisely right, but I have the topology kind of right. So there are really two fixed points, R equals 0 and U equals 0. And there's another fixed point, so the fixed points, the R equals 0, R star equals 0, and U star equals 0. And there's another fixed point, R star equals 0, and U star equals epsilon over B. So what you notice about these two, so near each fixed point, there's what you call the eigenvalue. There's certain eigendirections in which there's an exponential flow away from those points. So here there are two eigendirections, or just this and this. And the flow is away from this fixed point. So this point has two flows away from it. So we call a flow that's flowing away a relevant flow, a flow that's coming in an irrelevant flow. So this has two relevant perturbations. This theory, this point, has only one relevant perturbation. The other one always comes back to the fixed point. Okay. So now suppose I'm doing an experiment and I'm tuning some coupling constant. In general, when I'm tuning my knob in the lab, I'll be tuning both R and U. So I can apply this RJ argument. So here's my, I go along some line here like this. So this is the experimental tuning. So what will I do? So as I'm moving along over here, I'm going to go off to minus infinity. Now R going to minus infinity means that I have a double well potential, and therefore I'm going to break the symmetry. So I'm going to go off to minus infinity over there, like this, like this, like this. But then when I cross this point, I'm certainly going to flow off to plus infinity. So this is so as I'm tuning the parameter, this is my critical point. I will say, okay, at this point, certainly on this side, I go to plus infinity. On this side, I go to minus infinity. So when I'm tuning the knob, I just go along this line, and at some value of here, where U is some strange value, I'm going to see that suddenly I'm undergoing a phase transition. So my phase transition is here. But if I look at very long distance properties at the phase transition, I'm going to flow from here to this point. So in fact, at long enough distances, I will see the physics of this point. So that's the idea of universality. When you're near a second order phase transition, your actual value of U may not be the fixed point value. It's some value. Every experiment is a different value. But independently where you start, when you're at your critical point at long distances, you will end up here. So the U will be U star. So this is the value that's going to determine, the critical exponents, Planckian dissipation, the value of all these universal constants that I didn't talk about. So that's the idea how universality, scale invariance, and are all tied together in this very simple picture of, by hindsight, of course, of doing a rescaling transformation many times. Okay. Any questions? I think that's all I'm going to say on this topic, at least present.
Will the high order dependence on U and R change this flow in some way? Like if I start with
It could, but at least for small epsilon, we are guaranteed it won't. As long as epsilon is small, higher order terms will not change this picture. So that's really all Bilson and Fisher claimed. That's why they said critical phenomenon 3.99 dimension. Of course, you know, they didn't know how small it had. They didn't say how small. But there seemed to be at least some window. It turns out the window is pretty good. It's bigger than 1, but it need not have been. Yeah.
More questions?
Yeah.
So these equations are computed using these second-order diagrams, which you briefly mentioned that now they go up to like 6 loops.
Yeah.
What do we gain by going
you get,
to higher order?
Yeah, you get the critical exponents to a higher order epsilon. So you get the expansion in epsilon. There's also papers on something called the large order behavior. And then you can use some very sophisticated mathematical techniques to the epsilon expansion is an asymptotic series. It's not a convergent series. And so you can use something called Borel resummation. And yeah, the field theory book by Xinju Stan has a summary of all of it. The very sophisticated methods have been used to get more and more accuracy. I think, so the epsilon expansion was the best, but in the last few years, bootstrap method is beating epsilon. Bootstrap has gotten much more accurate than epsilon. So that's what, so if you wanted to compute any exponents, bootstrap seems to be the method of choice now. But if you want some physical insight as to what's going on, this is still a very good method. Bootstrap doesn't give you that much physical insight. It only works right at the critical point. This works everywhere. It's telling you something about not just the critical point, but also what's around it, and what are the fields and so on. Bootstrap doesn't tell you any of that.
So I was wondering about the
Well, so on the critical surface, so there's some critical surface here, which is just r equals 0. On the critical surface, it's a fixed point. So this tells you have 1 tuning parameter needed. To get on the critical surface, you have to tune 1 knob. Now, there are some fixed points, but you have to tune 0 knobs, like the SYK fixed point. So the SYK fixed point, if you formulate an RG, would mean that everything flows to the fixed point. There is no one direction running away. So the number of directions running away is the number of knobs you have to tune to reach the critical theory.
Oh, okay, but then we can still identify basically this running way top and like into the top or to the bottom. Basically, also we can identify them with phases, so we don't need a stable fixed point.
So in this case, we have a critical point, not a critical phase. Okay. So critical phases are generally more. This is a classical field theory, and in classical field theory, you generally don't find critical phases. But once you have fermions, once you have Chern-Simons terms, then you can get critical phases. The Fermi liquid is a critical phase. It's just the Fermi surface is very robust.
Okay, thank you.
I also have a question. So the kinetic term here is a little bit essential, no?
Yes.
So, for example, yesterday when you were doing Hubbard-Stratonovich, you actually put it by hand somehow. At some point, you do.
Oh, you mean the grad phi squared term? Yeah. So I was using.
So that's what people normally do. I mean.
Well, no, but if you went to, so for example, this graph here, even if you didn't have it, suppose I did the RG, I talked about this graph. No, which graph did I? Sorry. For R, I talked about this graph, U, and this gave me a delta R. But at next order, I have this graph. So this thing, if you do it, it will generate the kinetic term even if you didn't have it to begin with. It will generate a grad phi squared because this graph will depend on the momentum that's coming in. This one doesn't depend. So this graph will generate the kinetic term. So even if you didn't put it, it will appear in your RG. So you just kind of jump the gun and put it to begin with. Makes life a lot simpler. Similar for the SYK model. We put in the G prime because we know it's going to eventually appear anyway.
Okay. Another question is regarding the previous lecture. So at some point you had a V and you had a G, and at some point you said that, okay, V might produce this extra G.
Yeah, it's a very similar argument to this, although identifying which graphs produce it is not so easy.
Okay.
But just on symmetry grounds, we think there should be such a graph.
Yeah, but when it's about like putting by hand or something is coming naturally, I mean, the form of the functions doesn't matter much?
Well, I mean, it's a question of what is it you want to do. If you want to understand some general properties of the critical phase transition, like universal critical exponents or the structure of the phase diagram, you're much better off keeping all the relevant operators right away. But if you want to do a microscopic calculation for, for a particular Hamiltonian, for the Hubbard model, you want to know all the numbers, yeah, then you have no choice but to just do what's actually there. But then, you need big computers or something. So we're just saying there's certain quantities we can understand, some limited things by this perspective, where we just keep everything that's allowed by symmetry to begin with, and then focus on what's relevant and what's not relevant. That's the story of my life, really. Let me just say also, we can do this very quickly now for the Gros-Nouveau model. Let's just do it. And, as you can see, the hard part is just, the only thing we needed to know is what the graphs were, what the Bayer scaling dimensions were, and what the sign was. That's it. Once you knew that, apart from various other things, the structure was fixed. I mean, details, what the value of A and R and so on. We don't care. So let's do this for the Gros-Nouveau model. So now we can just add Dirac fermions. So you have psi bar d slash psi. Let's just do it in d dimensions for fun. And then you have, d mu phi squared plus r phi squared plus u phi to the fourth plus lambda psi bar psi times phi. Okay, so we know that the dimension of phi, what was it? It's somewhere there. 2 minus d or 2 minus d over 2. D minus 2 over 2. Dimension of phi is d minus t over 2. Okay, that comes from making this remains in bed. What is the dimension of psi? Well, now there's d, but there's only one gradient. So I'll give you d minus 1. Psi is d minus 1 over 2. It's different. Okay, so u, of course, dimension just like before is 4 minus d. And what is the dimension of lambda? So I'll just do it the way I know how. So you want to make this thing invariant. So this x will give you, so the lambda has to cancel the dimension of this. So you take the negative of x itself as dimension minus 1. So when you put a factor of d, that's minus d. You have to cancel it, so you'll get a d. You get this d from here. Then you have two factors of psi. You have to cancel these two factors of psi. You get minus d minus 1. That comes from here, twice that. And you have one factor of phi, and you have to cancel that, d minus 2 over 2. Okay, so let's do some algebra now. And I hope I got this right. What is this? So over 2. That's 2D minus D minus D, that give you D. And then I'll have minus my plus, yeah, minus D, sorry. And then I'll get plus 1 times 2, that's 2, and 2, so plus 4. So it's, when the dust settles, it's 4 minus D over 2. So we're in luck. This is beautiful. Again, we have to take, all we have to do is make 4 minus D small. And we take 4 minus D small, both U and lambda are small. So now we can do perturbation theory in both and get the next term in lambda. And again, you'll find a fixed point for lambda and U. So now you'll have a fixed point with one relevant direction, which is again R, and both lambda and U will go to fixed point value. So the scaling structure is almost identical to the 5/4 field theory of this Gross-Novo field theory. And it's very lucky that this went to 0 at the same D. If you go to many other field theories, you're not so lucky. One thing goes to 0 here in this dimension, the other thing goes that dimension, and then you don't know what to do. This is one of the few cases where it works. Yeah. All right, so what time did I start? I have to end at 1, right? All right, any other questions on this? Okay, so I'll say a few words about spin liquids because that's really what I'm thinking about these days. And many of you ask me questions, so I'll take that as motivation to say something about spin liquids. Okay, so now this is going to go on the up here. So really everything I've talked, well, not everything. I mean, today we focused on the symmetry breaking transition on the square lattice Hubbard model. And then, I should have shown this before. Yeah. Now we're going to, on the square lattice and yesterday on the honeycomb lattice. And then, of course, we talked about the SYK model as there's no symmetry there, but it's also an example of a system which has some critical Planckian behavior. So now I want to talk about the cuprates. So cuprates, there's one dramatic difference immediately, which I already discussed in response to a question. The difference is that where the interesting strange Planckian behavior is observed, there's no sign of any phase transition really. There is some kind of in high magnetic fields you get charge order, and there's a long story about fluctuations of charge order, but it's clear that when you're in the strange metal regime, no one's ever measured anything like a fluctuating charge density wave. It's just simply not there. And the various order parameters have reared their head over the last 30 years. Everything has fallen by the wayside. So how can we put the cuprates in the paradigm that we discussed today? So the key is to then understand what are the two phases on either side, okay? So on one side, of course, we have the Fermi liquid. This is well understood. The large Fermi surface, just free fermions to some extent. And I've already mentioned this Luttinger theorem that the volume in all the electrons are here, and this area should be just in units where the area of this thing is 2, the area of the occupied state should be 1 minus p. And it is indeed 1 minus p, as measured from experiment. You also know p from the Hall coefficient. It all really hangs together beautifully. Okay. Now this theorem, this Luttinger theorem I mentioned, was proved in Luttinger in 1960. And it's just some 10 pages of all kinds of Green's functions that no one can understand. No one I know really understand what's going on with all this stuff. But now there was a beautiful step forward by Oshikawa in 2000, where he understood this as some sort of anomaly. Again, I won't go through that, but just to know that there's a non-perturbative definition of the Luttinger result, which relates it to a certain anomaly associated with translational symmetry and charge conservation. And once you satisfy the anomaly, you can prove the Luttinger result for a Fermi liquid. So this 10 pages of Green's functions are reduced to just a few lines in Oshikawa's paper. And a beautiful argument. I could have done the tutorial on it. You don't need to know very much to understand it. And that's how we understand this today. Okay. But what's going on then on the left-hand side? Well, here you do get, just as you would get in the spin density wave state that I discussed today, a Hall coefficient of P. So the density of carriers is indeed P, as if you had long-range spin density antiferromagnetic order. But the trouble is, there is no antiferromagnetic order. People have looked for it. It's not there. In this entire yellow region, there's no sign of antiferromagnetism in neutron scattering. But there is still the Hall coefficient of P. Okay. So that's been one of the big questions in the field. What is this pseudogap? Okay. So we've argued for many years that it's somehow related to spin liquid. So what do I mean by that? So let me just go back here now. So the spin liquid is the following state. So let's start with the insulator, where you have the antiferromagnet doing this, just like on the honeycomb lattice yesterday. But as I did in my public lecture, imagine that the spins form singlets, and then there's a famous resonating valence bond state that's present, which has these spin-on excitations which carry spin but no charge. Okay. So this is a possible state of the square lattice antiferromagnet, but the actual state of the square lattice, which you can measure, again by neutron scattering, is this state. This is the state that you see at zero doping. This is the state that you see here, very beautifully. But when you dope it, it looks as if we claim that there's actually a spin liquid around. Somehow the act of doping takes it into the spin liquid state. So we want to understand not spin liquids, but doped spin liquids, or doped mod insulators. Okay, so yeah, so let me show you a few pictures of what you might expect. All right, so this is the Fermi liquid, where you have 1 plus P holes, just free holes, and then the area of this green region, in units with the whole area is 1 plus P over 2, because the factor of 2 is for spin. So at each momentum, you have spin up and spin down, so factor of 2 spin gives you area 1 plus P over 2. The density is 1 plus P. Okay, this is the antiferromagnet, where the area is nothing. There is no, it's an insulator, it's a gap in the fermion spectrum. Now you put in a few holes. This is what I described in the spin density wave theory. You can also do it by other methods. And I showed you this picture earlier. You get these 4 pockets of hole. And what is the area of each pocket? Now here's the key point, okay? When you have antiferromagnetism, you have broken the symmetry. So your unit cell has doubled, and your actual unit cell is this diamond unit cell. So really, the number of pockets is 2. You only have 2 pockets, because this pocket is the same as that. That's a reciprocal lattice vector in the ordered state. So you have 2 pockets, and the number of holes is P, and there's a factor of 2 for spin. So 2 for spin and 2 for valley or pockets, and so the area of each pocket should be P over 4. And this has been seen in experiment at very low doping. It is indeed P over 4. That's the answer. And it's just a free electron calculation that you can do. It gives you the right answer. Okay, no surprise. But this has long-range order, which is not present in the experiment. Okay, so what is the other possibility? Well, maybe it's a spin liquid. So I showed you the spin liquid of these resonating valence bonds, and I put in a few holes. Okay, now as I resonate the bonds, these vacancies move around. And you can see that as these move around, they're carrying charge. The charge is E. For them to move, charge E has to move around. Okay. But they're not carrying any spin. Spin is 0 everywhere. It's a set of singlets in which there's a vacancy moving. That's an object that has charge but no spin. It's what we call a holon. It's an emergent particle. It has if you write on a full theory, it carries a gate charge. It's emergent gate charge. It's only possible because the spin liquid is there and has long-range entanglement. Then you can have this holon particle in it. But this particle could be a fermion. And if it's a fermion, it will form a Fermi surface. Every fermion at finite density must form a Fermi surface as long as the global charge symmetry is conserved by the Oshikawa anomaly. So what is the area of this Fermi surface formed by this holon? Well, in this case, with many simple calculations, you will indeed again get 4 pockets of spinless particles. But now, see, what you see is that there are 4 pockets of spinless holons. And so the area is again P over 4, but for very different reasons. Because you have 4 valleys, but no spin. So there's a very different state, but somewhat unfortunately it has the same area as the spin density wave state. And in the end, this is all consistent with Oshikawa's anomaly because there's a background of these singlets that gives you 1. And then the Fermi surface anomaly gives you P. Okay. All right, so this is a possible state, but it has all kinds of problems with respect to experiments, which I haven't discussed. So now let me give you what I think is the correct state. So imagine the following, and then that in this state, I break a bond and create free spins. So since I'm breaking a bond, I'll play an energy cost of order J, the exchange coupling. So this won't happen in the ground state. But what can happen is that each of the can go near a holon, and then the holon can move around a bit like that. And that gains an energy T. So in fact, maybe the spin-on and holons will come together and form a bound state. And they'll get an energy T when they form the bound state. So since T is bigger than J, always, this will happen. So in fact, the actual objects which carry charge are these green objects. And this green dimer is this bound state of a holon and a spin-on. And that's, in other words, it's an electron. It has spin a half and charge E. Okay, so now everything can move around. You have this valence bond liquid again, but of 2 different types of the blue dimers and the green dimers. The blue dimers are spinless and chargeless, and the green dimers carry spin a half and charge E. And they have to be fermions in any reasonable theory because they have the same quantum numbers as an electron. Okay, so now these green objects can form a Fermi surface, which are holon spin-on bound states. And again, in various calculations, you form 4 bound states, 4 pockets, 4 valleys. But now what is the area? Well, I have 4 valleys and spin, so the area is P over 8. This is the key thing. All something you can understand from this very simple pictures. And if you want to do a more sophisticated theory, then you need to understand something about gauge theories and anomalies and so on. But the pictures really is how we understood it first. It's just very, very simple. You get a Fermi surface, which will now have an area P over 8. Okay, so now to summarize everything, let me skip that. There are 3 possible states that describe the underdoped cuprates. One is a state with antiferromagnetic order. This is the problem that there is no actual antiferromagnetic order, but Okay, let's just keep it alive. Maybe we haven't seen it yet. Some experiment will see it someday. There's this hole-on metal, which also has area P over 4. And then there's a state we call FL star, which has pockets of area P over 8. Now, the key point is that I gave these very simple pictures to figure out the area of these pockets. But the answers are robust. They're exact. In fact, they're quantized because of this Oshikawa anomaly. So this is kind of a beautiful thing, you know. Here we have, so that's, you know, somewhat like the fractional quantum Hall effect. Suddenly there's something that's quantized. Here it's just the area of the Fermi surface. I mean, it's not quantized in units of some fundamental constants, and quantized in units of the density. So you have to know the density. But other than that, nothing else. All right, so where are these pockets? So this has been any reasonable theory that anybody's ever come up with has some pockets, but they have never been seen so far. And this is where this Yamaji effect comes in, and I'll just stop with that. So there's this experiment. Oh, that was in the ordered phase. They do have they do have results at high doping when there's no order, but that shows I don't have that here. That just shows an arc. It doesn't show any pocket at all. Okay, so the evidence for pockets came in angle-dependent magnetoresistance experiments. First by Brad Ramshaw, and then this beautiful paper just came out just about a month, I guess, yeah, a month and a half ago. So they measured this particular compound, this mercury compound, at this point above in the pseudo gap, P is 0.1. And this compound has a very nice feature, is that along this axis, so here's the copper oxide, this is the square lattice right here, the blue circles are the copper sites. And it's just very simple stacking of square lattices on top of each other. It's really the only material that has that property. Other materials have a complicated crystal structure. You know, if you look at YBCO, there are these bilayers, and here the next square lattice is shifted by half a lattice spacing, and so on. Yeah, this is where the picture is. These are the arcs I was referring to. Okay, so they sit here, and they measure something called angle-dependent magnetoresistance. What is that? Well, you put a magnetic field at some strange angle, and you measure the resistance in this direction. So you put a magnetic field at angle phi theta, and then you measure the resistance along the z-axis. Okay, so if your magnetic field is pointing in that direction, your electrons will move semi-classically on an orbit like this, which is perpendicular to that. And, right. Okay, so, yeah, what is this warped thing, warped cylinder? Well, let's assume that there's actually a pocket, because every theory has them. So there are these pockets, and then they tunnel in this direction. So if they tunnel in this direction, there'll be a cosine band in the z direction. So these pockets, as a function of the momentum in the z direction, will warp. Okay. So that's this warped ellipse. You take a warped ellipse, and you take a cross-section of it. Now, in 1989, Yamaji pointed out something remarkable. So the important thing for the dispersion in the z direction in the presence of a field is the area of this cross-section. And what Yamaji said was that at a certain angle, which we now call the Yamaji angle, this area doesn't change to first order in the warping. It's the same no matter what kz you pick, which means you have a flat band or an infinite mass in the z direction, and which means you'll get a large resistance at that angle. So that's called, there'll be a peak in the magnetoresistance at the Yamaji angle. And then he also gave an expression from just knowing the Yamaji angle and this spacing, the distance between these copper sites, you can read off the area of the Fermi surface. So this paper, here's the data, here's the Yamaji angle, They took this model of ellipses. Here's the experimental observation as a function of theta and phi. Here's the theory calculation from the Yamaji theory. It just works beautifully. And from that, they can deduce their result. Well, this is a quote from the paper. This area of the pocket is 1.3% of the Brillouin zone. All right, they didn't comment much further what this meant. Anyway, so of course, when I learned about this paper, I did a very, very simple computation. I said, okay, what is P over 8? 1.25%. What is P over 4, which would come in the spin density wave or the other states? It's 2.5%. So this wins. And I should say that this factor of 2 was explicitly in this paper a long time ago in 2007, where we considered some very related physics. You know, we had P over 4 for spin density wave and P over 8 for some spin liquid type state. Anyway, okay, so this is, you know, it's really, I think, if this all holds up, I think the spin liquid picture of the cuprates is, you know, going to come back. It was abandoned for quite a while by most people. So it's very exciting that somehow spin liquid physics is really, seems to be really present here, it seems. The calculation, I should say, the calculation in this paper, the experimental paper is rather simple. We took a more sophisticated model in this paper here recently, and we confirm, I won't go into details, that again, for various reasons, neither the STW or hole-on metal agrees with the data, but FL star agrees quite well. Okay, I think that's all I want to say, so thank you for listening to this brief lecture about spin liquids.
Questions?
So do you now need to add this order back in to find Planckian dissipation? Or
Oh, yeah, okay. So then, yeah, so, right. So now the picture is that instead of a spin density wave state, we have this FL star state. And this is the phase diagram, the root of the phase diagram, where you have a FL star here and a large Fermi surface there. So how do you describe this theory? Okay, so I haven't discussed that at all, but you describe it, you describe it by introducing a Higgs field, phi. So the Higgs field is in some emergent gate charge that's associated with the spin liquid. And when it's condensed, you get the small Fermi surface. So it's very much like the STW theory, but it's got additional gauge fields. But once you put in disorder and randomness, you find that the gauge fields really make no difference. So the theory in the end turns out to be almost exactly the same, except the interpretation of phi is now different. The phi is not as, it's not a order parameter, it's a Higgs field. That's all.
and what leads to the suppression of the spectral weight for like a spectroscopist in the FL
And
star
the backside?
phase? Yeah.
Yeah, that's another recent paper. There we have to put in the gauge fluctuations. Okay. So we put in thermal gauge fluctuation, and they give you spectral weight just like this.
Okay.
Yeah, that's another recent paper that.
Thank you.
Yeah. And then eventually there's a superconducting onset of superconductivity here. Yeah, so this is the paper. No, is that the paper? Well, I cite it somewhere. Okay. Anyway, okay.
Any more questions? So let us thank once more. Well, we will ask to lock the door of the auditor. So if anyone wants to leave their stuff here, you can do it.